With the least square line, what this is oftentimes when you're looking at data from the real world, it's at the very best it's noisy, but oftentimes it doesn't really, for some reason, nature doesn't tend to go in actual lines. So here we have an example: accidental death rates for various years, and what the actual death rate is. I'm not sure exactly what this is related to. It's a book. It's a chart I pulled out of the book. Um, but if we take and we plot each of the years to the death rates, we're going to see a certain pattern. So I'm going to go ahead and plot that stuff now. In 1910, we have a death rate of 84.4. Let's see, that's 90 up here. 84.4 would be about here, and so on. I'm gonna go ahead and skip ahead and until I have the rest of these plotted. All right, so this is what it looks like. I just took those those individuals and those individual values and plotted it here. And you can see the death rates are definitely falling. And it looks like they're actually falling at a fairly consistent rate. Now, it doesn't fall at the same rate every year. Obviously, it doesn't even always fall, because you can see it fell here and then it raised back up, and then it fell for a couple of years and then it raised back up again. It fell a few more years. But in general, it looks like the data is falling. And it actually looks, roughly like this is a line. Looks like that line right there actually fits the data pretty well. Now, the question that we're concerned with here with the least square line is, how do we find this line? And what's to say that's the best fit line? What's to say that I shouldn't be just a little bit more like that? Maybe that's a slightly better fit. How do we find, how do we actually agree upon a line that is that's a good fit? So what this least square line does, it's you can see there's a big complicated formula to actually find it. What the least square line does is it basically says we're going to measure the distance, not quite the distance, but the vertical distance off of the line for each of these. The vertical distance is a lot easier to calculate. That's why it's used. But the vertical distance off of the line for each of these points, and then we're going to square that distance, that's the square, and then sum all of those values up. And looking at all the different possible lines, whichever one has the total, the sum of all those squares, whichever line has the sum of all those squares being the least, that is what we're going to be calling the best fit line. And this is where this terminology comes from, this least square line. We're taking the squares of those distances, well, we want the least of the squares of those distances. So the actual method to compute that, if we're doing this thing by hand, is a little bit complicated. Now, I'm going to be showing you how to do these things on the calculator, but just so you can gain an appreciation for what the calculator's doing, I'll explain what's going on here. So this formula here, you can see there's a formula for the slope and a y-intercept of that line up there. These symbols right here, this is what's called a sigma, and for instance, if I was to look, if I did a sigma x, what this would do is it would look at all the x coordinates of all the different values, and it would sum all of those up. If I did a sigma y, it would look at all the y values, and it would sum all of those up. If I did a sigma xy, what it would do is it would take x times y, so it would take whatever the x coordinate is times the y coordinate, and then it would do this for each of those points and add all of those things up. So that's what this sigma x, sigma y, sigma xy, that's all that stuff means. And you can do other things. You can see here there's a sigma x squared. It's going to take the x coordinates, square them, and then add all of those up. All right. So if you're doing this thing by hand, you kind of have to go through and do all these individual parts. Now, because we're going to be doing things like sigma x squared, and you can see the x's are fairly large, almost 2,000. If I was to square that, I would get, almost 4 million. This is another case where it's handy to move off, to move where our origin is. So the x's in this case are going to be the number of years after 1900. So this right here, the year 1910 becomes an x value of 10, and so on. Again, you need to be careful when you're plugging stuff into the calculator to account for shifts like that. But in any case, If you're doing this thing by hand, you would want to go through and write up a chart similar to this. You can see there's x's, y's, x times y, because that's one of the values that shows up on here, x times y, sigma xy rather. Sigma x squared shows up on there. Sigma y squared shows up on, oh, it shows up on a later chart, but if you're doing all this, you might as well do that one. All right, so if we were doing this by hand, I'd go through and add all these up and get some number here. I would take x times y, which would be 844. I'd take x squared, which would be 100. I'd take y squared, which would be 84.4 squared, whatever that ends up giving. And through the magic of editing, yeah, look at that. I filled out the whole chart. Well, kind of. You can see all the different values are filled out here. The sum of all your x's is 550. That 844 that I wrote in is right there, that 100, and so on. And you can figure out the sums. If you're doing this by hand, you can see it quickly becomes a fairly tedious process. I've seen people do this in spreadsheets. You know, if you want to do this in LibreOffice Calc or Microsoft Excel or something like that, it's entirely possible to do that. I will be showing you a method, or I'll be creating two separate videos. I'll be doing one for the TI-36X Pro and one for the TI-83. These are two different calculators that I personally have, and so it becomes really easy for me to show you examples on those. Other than that, you might have to look up other examples. So these are those formulas again. If we were to actually compute how we would do these formulas, is I would take I would have to plug in all these values. N is the number of data points that we have. So this would be 10, because there's 10 different data points. Let's see, M equals sigma xy, that's this value right here, 28135, minus the sum of all my x's, which is 550, times the sum of all my y's, which was 595.5, divided by 10 times the sum of all my x squared values. The sum of my x squareds is right here. This is 38500. And minus the sum of all my x's, which is 550, squared. You can see this squares on the outside of the parentheses, so I did 550 and then square it. And if I plug all that stuff into the calculator, it's going to give me some value. Let me go ahead and do that. There we go. Since I'm plugging this into the calculator, I'm doing this by, well, arguably by hand. Obviously, I could do that on this calculator, but I'm wanting to show you how it will work. I'm going to be needing to put parentheses around the top part of this and around the bottom part. You could alternatively compute those separately, but I'm kind of a fan of just doing it all in one line and adding the parentheses where they're needed. So 28135 minus 550 times 595.5, close the parentheses because that's the top part of my division, divided by, I'm just using my keyboard to type because it's a lot faster than doing it by hand, using the mouse to click, minus 550 squared. And we end up with negative 0.5596. Negative 0.5596. Now, let's look up here. It is a negative slope. Oops, that's right, it's on a previous page. It is a negative slope, which is expected, and it's about a negative 1/2. So, you know, negative 1/2, negative 0.55, whatever. Negative 1/2 would be negative 0.5. If I was to go down, remember slope is rise over run. Negative 1/2 would be approximately, if you went down 10, you would have to go to the right 20. So if I was to go down 10, so from death rate here down 10, I'd have to go to the right 20. I'd have to go 20 years. I'd have to wait 20 years for the death rate to decrease by 10% or whatever that is. And that actually looks fairly accurate based on this this kind of sketch I drew up there. So I'm actually pretty happy with the negative 0.5596. As you can tell, there's a lot of numbers to deal with here. It's really easy to make a mistake if you're doing these things by hand. I would encourage you, if you feel so inclined to do them by hand, definitely show me all of your work. Because if you don't show me your work and you get 0.5791 or something like that, I have absolutely no idea where your numbers came from there, and it becomes really hard for me to figure out how to give partial credit there. When I can't figure out how to give partial credit, I tend to just not give partial credit. Now for my y-intercept, we're going to be using our slope as part of the y-intercept. B equals the sum of all my y's, which is 595.5, minus my slope, which is negative 0.5596, times my x, sum of all my x's rather, 550, divided by n. It's 10 because there was 10 points here. Again, this is something I would plug into the calculator. Let's see. I'm subtracting a negative number here, so I'm just going to change that to addition. So on the first top part of my parentheses, I'll do 595.5 plus 0.5596 times 550. Close that off because that ends my parenthesis, the top part of my division, rather. Top part of my fraction, divide that by 10, we get 90.3. Equals approximately 90.3. Again, I'm going to go back. Oops, that's not what I meant to press. I'm going to go back here and verify. Actually, that looks quite accurate. 90 is right here, and 90.3 would be just slightly above that. So I'm actually really happy with the numbers that came out here matched my drawing quite well. So the last thing I'm going to talk about with this, actually I'm going to make this a separate video because I'm sure I lost some people while doing this.